And the book, what it does a lot of times, it'll have the it'll start a problem on one page and then go to the next page, and that's exactly what they did here. Don't exactly like that process. So I transcribed the previous page problem right down here. Wrote the equations of equilibrium about point G, or the moment, excuse me, just the moment alone. I didn't write everything. Because it eliminates these two forces, and we only have perpendicular forces. Real easy to calculate the moments. We have an FBC going counterclockwise, so that's positive, 3 FBC in Newton meters, 3 meters times FBC in newtons. And we have A at 400 newtons times 3 meters, or 1200 Newton meters, 1200 Newton meters clockwise, negative. 300 newtons at 4 meters clockwise, so that's also negative, about point G. Negative 1200 about point G. When you solve for FBC, it's 800 newtons. So we've got that part. Now we can take the moment about C. Now, remember, you can choose any point in the universe to take the moment around. You don't have to choose it around something on the diagram. So this is a nice trick. This is a good trick to kind of keep in the back of your mind. Oh, I can simplify my problems if I do this. That means we have FGE counterclockwise at 3 meters. There we go, right there. And this force is acting along the same line of action. FBC, we don't have to worry about FBC. We don't have to worry about AX. We don't have to worry about FGC because they're all concurrent at this point, at point C. We just have to worry about two forces, 300 newtons and FGE. And that'd be 300 newtons times 8 meters, and it would be negative because it's going clockwise. And we find out FGE has to equal 800 newtons. So that's FBC, FGE, FBC, FGE, yeah, horizontal, horizontal. The only thing left is FGC. So we can look at just one component in the y direction. Another trick the book did, which is really cool, is something they did that's cool, is that they had two moment equations and a force equation. They didn't just go for the forces. It was it's some insight. It's insightful. They took some simple approaches. And it's good to see that kind of thing. Okay, Fy, sum in the y direction has to equal 0. We just have the 300 newtons here, and we have minus FGC times the sine of this angle, which is, cosine of this angle, which is going to be 3/5. This little triangle helps us remind us of the sine cosine. Sine would be 3 divided by 5. Sine of this angle right here. Get my brain in gear. Get my tongue in gear. Cosine. Cosine of that angle right there. FGC cosine. The vertical component. And then the only other vertical component is right here. FGC cosine of that angle, which is 3/5. 300 newtons positive, negative 3/5 FGC. FGC is 500 newtons. Okay. So, compressive and tensile. When the arrow is pointing away from the beam, we've got tensile stresses. So the arrow is pointing away from the point along the beam. Arrows pointing into the beam, in this case, FGE, compressive. If you might have insight that ahead of time, it's possible to tell by inspection the directions of the unknown forces. You might not see that. Just remember, if you get a negative number, it means you got your directions reversed. You thought the direction was one way, it was actually the other way. Okay, trusses in space, 3D. So the way we go about it is very much like 2D. It's just more complicated. The loads at all the joints. Joints are modeled as pins and members to force members. So here's an example here. Forces in the members of this space truss. And so we have point B, ball and socket. So we can have forces in 3 directions. Oops, my X is kind of a wonky there. I won't worry about it. B, oops, my Y is kind of wonky. My X. Let's fix it. The way the book drew the XYZ coordinate axes are a little bit different. So than what we're used to. And hopefully the author, whoever shows us the solution to this problem, has some insight why they did it that way. So this would be BZ, BY, BX. Okay, this would be another ball and socket, so it could have 3 directions of forces. EY, EX, EZ. Another ball and socket, 3 directions. Now this one, at least, we know it's vertical because we have a 2-force member right there. So we just have D in the Z direction. Might be good to remember it's in the Z direction. Let's see. This is a 2-force member too. So this force here would be in the Y direction. CY. Because this is a 2-force member and it's only along the Y-axis. 2-force member only along the Z-axis. And we cannot eliminate BZ because we have a 2-force member here. So we're going to have a reaction force here. The only trouble is it's going to be but we also have an applied load at this joint. So we have a force 45 degrees. It does mean BX and BY would have to be equal though. That will be a simplifying assumption. Okay. So we look at this and at this point, P, that's your 4 kilonewton load in the negative Y direction. My pen tablet, so, you know, it's sometimes hard to write, computer write. Okay. FAB, it's a two-force member, so we have this. FAC, two-force member, so it's only in the K-hat direction. So we're looking at this joint right here. Okay. 1, 2, 3. Now we have this force, E to A, which is going to be tricky. Force EA, it's a two-force member, so we can write it as a force times the unit vector along this, right there, down to E, from A to E. And we have to calculate that unit vector. So let's go ahead and stop the video here. We'll go through that.